Differential amplifier is a voltage suppressor circuit that produces output voltage proportional to difference in two input signals. These input signals can be inverting and non-inverting or grounded signals. Hello, my name is Muneesh. I am a trainee at Pine Technic Academy. I have completed my BTech from North Cap University, Gurugram. I have completed a lot of projects in analog circuit and layout such as current mirror, differential amplifier, delay circuit. In layout, I have completed differential amplifier, analog inverter, C flip-flop and 2-in-1 mux. Today, we are going to look at one of such projects, that is differential amplifier with single-ended output. Why do we need a differential amplifier? So, we need differential amplifier in a circuit where electrical noise is very strong, where a small amplitude signal can get corrupt easily. In those scenarios, if we use common source amplifier, that will amplify the input signal as well as noise with it. That is undesirable for us as a designer. So we use differential amplifier as it states that the unwanted noise will be coupled to both the terminal of the differential amplifier equally and thus get rejected, and only the difference of the inputs will get amplified. So let's look at the circuit. So this is our design for single-ended differential amplifier output. So here we have 6 NMOSes. So this is our single-ended differential amplifier output schematic. Here we have 6 NMOSes connected in this sequence. So we have two signals, VIN1 and VIN2, which is going into our differential amplifier. We are taking output from our VIN2 side. So for this circuit to work, it should be in saturation region. Before that, we have to look into what is the configuration of our design. So here we can see that there are two current mirrors connected in our design. One is at the top and one is at the bottom. So at the top one is working as a active load, that is this providing resistance for our design, for our differential amplifier, to act as a common source at one side and common source at the another side. And this bottom one is acting as a current source. Why we are requiring current source? We are requiring current source so that voltage change in VIN1 and VIN2 doesn't affect our drain current, which is going through this NMOS 0 and NMOS 1. So for that, we are actually limiting our current to this particular current source. So for this, let's just check if all of these transistors are in saturation region. For this, we are going for DC analysis, and we will check if these are in saturation region and if their operating point are set. For that, we're going to DC, save DC operating point, OK, and then just run ADL. After this, we are going for the annotations. Here we can see the annotations. So in this annotation, you can see that all of the NMOS are in saturation region, and here we can also see the current. So here our current should be close to 5 microampere and here should be 10 microampere. So our ID current is 4.8 as it divided into a two part, as current basically divides into equal value if it is going to a branch. So let's just go for the trans analysis. Trans analysis, we are going to choose trans analysis and give stop time as 10 milli. After this, we are going to select the signals such as VN1, VN2 and Vout. Now we are going to run this and see the output. So we will get output like this, where our Vout starting from 0 and going from 1.5 volt and 1.5 volt plus side and negative side of the graph. We can actually see that Vout is following our Vin as the common voltage are getting subtracted. So let's now look at the AC analysis. For AC analysis, we again go for AC analysis. For choosing analysis, and then we select AC. Here we are checking in frequency domain. So in frequency domain, we have to select the sweep range from 1K to 100K, or you can go for 300K and then run the ADL. Here you can actually check how much current we are getting. Now in this window, we can actually see our AC analysis. to check our dB, we go for dB20. So here you can actually check what is the dB value of what is the gain of our design, which is minus 35 dB. This is the gain of our single-ended output differential amplifier. So now let's check our DC analysis too. So in DC analysis, we are only going to check our DC values. So in here we are selecting components such as V in 1 because it is following V out is following V in 1. So here we are going to select values such as minus 5 to 5 and run the design. We get something like this, where V out is like 1.5 going from 1.5 to almost 1.8 and even 2, whereas our V1 is going minus 5 to 5. It is cross-sectioning at 1.8. That's all about single-ended differential amplifier circuit. Thank you everyone. If you have any suggestion, please comment below.